So far it might seem like we're covering a bunch of physics, and you might wonder what any of this has to do with actual chemistry. Don't worry, we'll be bringing atoms into the equation in just a moment, but first you need to understand how quote-unquote normal sources of light work. There is no single frequency of light that corresponds to white light. Rather, white light is the result of combining all visible colors of light together. If you take a source of white light, like sunlight for instance, and split it apart with a glass prism or even a suspension of water droplets in the sky, the different wavelengths of light will bend at different rates, producing the full spectrum of visible light spread out by wavelength, also known as a rainbow. While sources of white light contain essentially all wavelengths of visible light without any missing wavelengths, this is very different than the light produced when atoms are energized. When an atom is energized, or in technical terms, excited, it instead will emit a series of separate wavelengths. This is called a line spectrum because if these wavelengths are projected onto a dark background, the lines appear only at a limited number of positions of the visible spectrum. The emission lines of sodium and neon can be seen on this slide. The colors seen in each spectrum are the types of light emitted by each atom. The dark areas are all the wavelengths where there is simply no light emitted by those atoms. One instance where you might have seen this phenomenon is shown here. In many public outdoor areas, such as parking garages, they use low-pressure sodium lamps to light up the area at night. These bulbs are used because they're energy efficient, but they work by exciting sodium atoms, which, as you can see along the top of the screen, only emit two very closely spaced yellow wavelengths of light. When we perceive an object to be a certain color, it's because it reflects that color of light and absorbs all of the other colors. Our eyes detect the reflected light, which our brain perceives as a certain color based on its wavelength. Now, the cars shown here are actually different colors. The one on the left is red, and the other one is black. But you can't tell under the sodium vapor lamp light because there's no red light available for the red car to reflect. As a result, we don't see it reflecting any light, so it too appears black. Okay, but why do atoms emit line spectra rather than regular white light? One of the first attempts to explain this observation was by physicist Niels Bohr, who postulated a model of the atom with a nucleus at the center and electrons orbiting in circular paths around it, kind of like planets orbiting the sun in the solar system. This model would explain how the energies of electrons are quantized. They can only exist in one of several discrete orbits, which in turn would explain why atoms have quantized line spectra rather than continuous emissions with all wavelengths of light. It's also the most familiar model of atoms in popular culture. Unfortunately, it isn't correct, as we'll see later. Nevertheless, this model could accurately predict the emissions seen in the spectrum of hydrogen atoms. When an atom is excited, its electrons move into higher energy or further out orbits. When a high-energy electron subsequently falls into a lower energy orbit, the decrease in potential energy is balanced by emission of a photon with an equivalent kinetic energy. The larger the energy difference between the higher energy orbit and lower energy orbit in one of these transitions, the larger the photon energy and hence the higher its frequency. An energy diagram shown here can account for the observed transitions. Each energy difference between orbits corresponds to a photon energy observed in the emission spectrum for hydrogen. This includes the Balmer series, which contains all of the visible wavelengths emitted by excited hydrogen atoms. All of these transitions correspond to electrons falling from higher energy orbits down into the n equals 2 or second orbit. There is, in fact, an equation that describes all of the observed transitions in terms of the orbit numbers, shown here. When an electron drops down from a higher energy orbit n down to a lower energy orbit m, the wavelength of light emitted can be calculated from the equation here. This was first discovered by Balmer in the context of the visible lines in the hydrogen line spectrum, where m is equal to 2, and later broadened by Rydberg to fit all of the ultraviolet and infrared emissions as well, where both m and n could be any whole number greater than or equal to 1, and where n is greater than m. The constant that gives the wavelengths from any transition, the Rydberg constant, is shown here. All this overlap between the behavior of electrons and light got a scientist named de Broglie thinking. If light can behave like matter, like it does when we observe its quantized nature, then could matter itself also behave like light, in other words, like a wave? The answer, as it turns out, is yes. In particular, on very small scales, like those of individual atoms, matter such as electrons or other particles can be described in terms of wave-like properties. Already with that discovery, there's some pretty severe discrepancies between the Bohr model and what was known about electrons in atoms. By the 1920s, Schrödinger brought together the developments of quantum mechanics, such as the behavior of light from earlier, with this wave-like behavior of electrons, producing the quantum mechanical model of the atom. Furthermore, Heisenberg developed the uncertainty principle around the same time, which asserts that the location or path of a particle, like an electron, can't be determined with certainty, which is completely incompatible with the nice orbits of electrons from the Bohr model. Based on Schrödinger's model, electrons can be described by a wave equation, which when solved produces a wave function, also known as an orbital. This wave function gives us the probability of finding an electron in a given region of space around the nucleus. In the process of solving these equations, three parameters, known as quantum numbers, appear, whose values determine the behavior of particular electrons. And by the way, solving the wave equations for electrons is not at all something we'll be doing in this class. That's something you can do if you take Chem 3541, Physical Chemistry. Let's take a look at these quantum numbers. The first, n, is the principal quantum number. This describes the size and energy level of the orbital and is commonly referred to as the number of the electron's shell. It must be a positive integer value, and as its value increases, so does the electron's energy and distance from the nucleus. Next, we have the angular momentum quantum number, L. This defines the 3D shape of the electron's orbital and is commonly called the subshell. For any particular value of n, the possible values of L are integers between 0 and n-1. Rather than specifically referring to the subshells as L is 0, L is 1, etc., it's far more common to use the subshell notation at the bottom of this slide. For L values of 0, 1, 2, and 3, we represent them by the letters S, P, D, and F respectively. We won't encounter any examples where we need to consider subshells beyond L is 3. Our third quantum number is the magnetic quantum number, m sub L. This number defines the spatial orientation of the orbital in question. For any given value of L, m sub L can be any integer between negative L and positive L, including 0. This gives rise to 2L plus 1 different possible values. This table shows the allowable combinations of the three quantum numbers for the first four shells. If you remember how the allowable values of each number are determined, there's not much point in memorizing this chart. However, I will point out the notations for each orbital listed here, the numerical value of n followed by the letter corresponding to the value of L. So for instance, for n is 1 and L is 0, we have a 1s orbital. These are the names by which orbitals are almost universally referred to. You'll recall that when we discussed the electron energy level transitions for hydrogen, each energy state had a value of n is 1, n is 2, etc. This corresponds to the principal quantum number of the orbitals in the quantum mechanical version of the hydrogen atom. The spectrum for hydrogen was relatively simple and given by a single equation because the energy transitions only depend on the values of n. In other words, the energy of a hydrogen atom's orbital doesn't change between, say, an s and a p orbital with the same principal quantum number. This is not the case for atoms with more than one electron, in other words, every single element on the periodic table other than hydrogen. For atoms with two or more electrons, for any shell number, the s orbital will be lower in energy than the p orbital, which will be lower still than the d and f orbitals. In fact, this effect is significant enough that there is some crossover between shells. For instance, a 3d orbital in a multi-electron atom will be higher in energy than a 4s orbital. To understand what's going on with multi-electron atoms, we need to know some more information about the shapes of orbitals, or the spatial distribution of where electrons have a high probability to be found. The simplest to describe are s orbitals, which are spherical in shape. A 1s orbital is a simple spherical shape, and higher s orbitals are nested spheres of probability with nodes in between them. A node, generally speaking, is a point on a standing wave where it has zero amplitude. Because the wave function of an electron determines the probability distribution of its location, these nodes are points in space with zero probability of finding an electron. This graph plots radial probability of electron location versus distance from the nucleus for the 1s, 2s, and 3s orbitals. You can see that the 1s orbital has a high probability of finding the electron close to the nucleus. The 2s orbital corresponds to two regions of probability, one closer to the nucleus and one further away, separated by the point where it touches the x-axis at around 100 picometers, the node between these two regions. And for the 3s orbital, we can see our three regions of probability separated by two nodes. Note also the general trend of electrons being further away from the nucleus as the value of n increases for each orbital. Next, we'll look at the shapes of p orbitals. Here we see the three distinct 2p orbitals, which are sometimes described as dumbbell-shaped. These all have the same shape, since they all have the same values of n and l, but different three-dimensional orientations due to the differing values of m sub l. Each one has a nodal plane at the nucleus, and can be designated as to which axis it falls along in 3D space, x, y, or z axes, corresponding to m sub l values of -1, 0, and +1, respectively. Orbital shape complexity and the number of possible orientations increases as we get to d and f orbitals, so you won't need to be familiar with these shapes or their designations. Just know that, based on the number of possible m sub l values for each, there are 5 d orbitals and 7 f orbitals per subshell. The shapes of orbitals have implications for the energy associated with each subshell. This is due to the phenomenon of electron shielding. In a multi-electron atom, all of the electrons are attracted to the positively charged nucleus, but repelled from the other electrons due to their mutual negative charges. As a result, each electron, especially the outermost electrons, experiences a smaller net attraction to the nucleus of the atom than it would without the other electrons present. We can quantify this effect in the effective nuclear charge, or the net attraction of each electron to the nucleus when we account for the shielding. Looking at a radial probability plot for the three subshells under n equals 3, the 3s, 3p, and 3d orbitals, we can see that the s orbital has the highest probability of holding an electron close to the nucleus, while the probability lowers for the 3p orbital and is even lower still for the 3d orbital. This means that the orbital types are affected differently by the electron shielding in a multi-electron atom. When we reduce the probability of an electron existing close to the nucleus, we increase its shielding and decrease the effective nuclear charge felt by the associated electrons. As the effective nuclear charge decreases, the energy of the electrons goes up. This explains why, for a multi-electron atom, the 3s, 3p, and 3d orbitals don't have equal energies like they do for a hydrogen atom. For the single electron in a hydrogen atom, there are no other electrons present to cause shielding, and so no energy difference between these orbitals.